will see the benefit of the latch there.
Okay, sir.
Okay. So now this is the oldest latch. Do you see? This is a latch. When CK is high, D or Q follows D. When CK is low, Q is independent of D. Are you able to see this?
Yes, sir.
Yes, sir.
So what are the challenges and what are the benefits of this latch?
Sir, we are feeding to the diffusion part of the transistor. That is an issue.
Okay, diffusion input. And so this is a benefit or loss?
Loss.
Loss. Okay. What else?
Sir, two latches in parallel, if the output is shorted, then because this is a pass transistor, we can have like input being driven from the output kind of thing.
Okay. The output can end up driving the input. Good. Very good. What else?
So VT drop.
VT drop.
VT drop. Very good. See the first thing. Let us look at the benefit. The benefit is that it's just one transistor latch. Just one transistor. So it's tiny and also very low clock load. But cons, oh, as you just said, VT drop, output, input on diffusion, output being able to drive the input and all that. Back driving, everything. All these are losses or cons of using this kind of a latch. And output noise sensitivity also. So lots of negatives. So what do? We change the design. We say that, okay, let us use a transmission gate latch. At least VT drop wala problem solve hoga. So VT drop wala problem solve hua, but what happens? Now I require an inverted clock also. I'm still on diffusion inputs. I still may have back driving. All those things will still remain, though VT drop problem is solved. So I want to solve other problems also. So what do?
Cascade with inverter.
Yeah, so we say that, okay, let me put an inverter at the output. Now the output cannot drive the input. Or let me put an inverter on the input. Now the input is no longer driving a diffusion. So what happened? I have restoring output, then no back driving, and fixes either output noise sensitivity or diffusion input problem. Are you able to see this? But either of those two, not both of them. So what would be a better solution then?
Sir, how is the back driving problem getting solved here?
So now tell me, can Q drive D? Nahin, na?
Can we use?
D is either going to a gate or Q is going to the drain and cannot transmit it to the X node over here. So Q cannot drive D now. So back driving is not a problem now.
Sir, can I use two inverters at the input, one at the input and other at the output to fix both issues?
Yeah. Can we use both inverters at both input and output? Yes, we could. So see, we are using it over here. Input is also inverter, output is also inverter. More importantly, even before that, just because this latch is still dynamic in nature, you see, the charge on node X is sensitive to noise. This latch is still dynamic in nature. When the Q bar will go off, when this transmission gate will go off, then this Q bar will be floating. So first, an important thing is to solve this problem first. So we say, okay, we add feedback. We add feedback so that there is no dynamic node now. So I've reduced the sensitivity of the output. However, in this setting, there is back driving risk. Therefore, what do? We say feedback bhi dalte hain and we add the inverter on the input also. And you will see it fixes diffusion input problem also. This is non-inverting, and there is like if you size it, no, in fact, either sizing ki baat hi nahi aayi. When you want this path to be active, this path will be off, so there is no backdriving also. Are you able to see this?
Sir, can you explain this? Actually, it's getting after that. For example, when we had only one inverter cascaded, it solved our problem for the back driving one. But
Yes.
after that, what we did exactly?
So even when that one inverter was put, do you realize that there were nodes which were not driven when the clock was off? There were floating nodes there where the charge was stored on some gate or some capacitance.
So if the inverter was at the output, after the transmission gate, then I won't be getting floating, right?
The output is floating now, no?
Here in the second one is floating, but the above one is not floating, right?
Above one X is floating.
Okay, right. Okay.
Therefore, output becomes floating.
Yes. Okay.
है ना?
Sir,
So
why can't
floating
we
things
use,
are important to fix first. So therefore, we first talked about adding a tri-state.
why
Sir?
can't we use the weak keeper sir over there or level restorer in between to make sure that we won't float that exposition which we were instead
Yeah.
of
So that
tri-state.
is what feedback is, na, Vaishnav. Look at this. What is this? Level restorer for the dynamic gate. Level restorer was a simple PMOS. For a static gate, for an inverter, the output can be both 0 and 1. So the level restorer has to be an inverter. That is what we have put. Na?
Yes, sir. Understood.
We've done that only.
Yes.
Just that we've used a tri-state over here. Why did we use a tri-state and not a simple inverter?
To make the driving of X easier for me. If it was a latch, then inverting it through D would be a challenge.
Yes. If this was not a tri-state, if it was an inverter, then this inverter would be driving X and this D will be driving X. And it will be difficult to write into X.
So can you elaborate exactly why we're doing tri-state in some inverter? I mean, could get it.
Okay. Let us say we said that we just want to put a level restorer. That is what was asked. Vaishnav said, let us put a level restorer. So for an inverter, the level restorer would mean a feedback inverter. Instead of half latch, we put a full latch. Am I right? Hello. Have you understood this part? Why do I need a full inverter and not just a PMOS?
No, sir.
Sir, to have both 0 and 1 stable at X position, sir.
See, in a dynamic gate, your output could only be 0, could only go to 0.
Yes, sir.
So you always knew that if the output goes to 0, then that is when I need to, or when the output remains 1, that is when I need to maintain the output there.
Yes,
In
sir.
this case, it's a latch. Output
Okay,
could be 0 and 1 both.
Okay.
So you need to maintain both 0 and 1. So you need to put an inverter.
Yes, sir. Yes, sir.
Is it clear now?
Yes, sir.
Now, if I put an inverter, what happens? This, let us say this was 0 earlier. So this will drive this at 1. Am I right?
Yes, sir.
Now, when I turn the clock on, D wants to write into this.
Yes, sir.
But this inverter is driving back.
Yeah, okay.
So D wanted to discharge this, but this inverter is also charging this up.
Yes, sir.
So this is a fight condition. है ना?
Yes, sir.
Now, if we put a tri-state, what happens? If I put a tri-state over here, what happens now?
Sir, we are synchronizing the input to X appropriately so that I won't get in a condition that at a time these both get into a conflict.
Yes. So when this path is active, this would be off. Look at it. When phi is equal to 1, this NMOS is on, phi bar is equal to 0, so this PMOS is also on. D is trying to write to X. But when phi is equal to 1, it is going to the PMOS over here. So this tristate will no longer be driving.
Yes, sir.
Huh? So now you've removed the fighting condition. So we've actually done the level restorer stuff only. Just made it safer.
So can't it also be done by using a feedback inverter, but a smaller feedback inverter, so that it doesn't fight back?
Which feedback inverter?
So we earlier drawed like that SRAM type cell. So this bottom inverter, which is used for feedback, we can size it so small that it doesn't fight back.
Yeah, but then you know about variations, no?
Yes, sir.
So what can variations do? Variations can make your this inverter very strong.
So how strong? I mean, I am designing it to be so small. So
Yeah, but even then, what's the harm in putting it into a tri-state? You are guaranteeing functionality. Independent of any variations, you are guaranteeing functionality when you put it a tri-state. Is it not?
Yes, sir.
That's why.
So clock load would decrease.
I know, but functionality is more important.
So what's the internal structure of this tri-state buffer?
Oh, you don't know the tri-state buffer?
I don't know, sir.
Okay, so tri-state buffer, sorry, I assumed that आप लोगों ने tri-state buffer तो देखा हुआ है. So if I say this is input and this is output, then there will be CK bar going over and CK going over here. So that when CK is equal to 1, this acts as an inverter.
Okay. Yes, sir. Yes, sir.
So it's just an inverter only. We just clocked it.
Yes, sir.
So that it does not fight back the forward path when needed.
Okay, sir.
Yes.
So I mean, for example, in the simple, when we had only cascaded the inverter after the X node, and I know that the X is basically my floating high. So for example, sir, I'm only concerned with the output when it is a high impedance one, because zero to hamara zero, it's good, like, right? Zero would be.
Why is zero good? There is a metal running next to this node X, and it is going from 0 to 1. It will couple a charge 1 on this X.
Okay, so but like, is it, I'm considering the kind of worst case, like it will going above or below the VDD by 2 position.
See, Raghav, you are a designer. You cannot leave anything to chance. I just gave you a failure mode. You cannot think beyond that now. If the circuit can fail, you can no longer use it.
Okay, so like
you have to find another solution.
So like we can't rely on the cascaded inverter to restore the kind of
cascaded inverter.
So this inverter only, like simple single inverter that we've cascaded after the transmission gate.
How will it restore? It is not even driving. If you have just one inverter on the output, no feedback, how will the output of the inverter restore the input?
No. So if it is if the variation is within the noise margins, then it can restore, right? Then it can.
How? In the dynamic gates, we looked at the dynamic gates before this system.
Yes,
Why
sir.
did we look at the dynamic gates first? Because in dynamic gates, we saw that there's nothing that can help you to restore.
Yes. Sir.
So what will restore over here? Tell me.
No, so I'm thinking, for example, if X is there, if X is at 1 and it suffers kind of leakage, so its voltage will drop. But if it is if the drop is within the noise margin of the inverter, then only.
How do you control it within the noise margin?
Okay, right. That is the challenge. Yes.
No, you can't control it. No, you to control it, you have to put this kind of a feedback.
Yes, sir. Okay. Yes, sir.
Okay, Rajneesh.
Sir, when this clock is 0, sir, that is when this transmission gate is off and this tri-state feedback, this turns on. Sir, any value on this Q bar, sir, may affect this X. Sir, still those has advantage, but this may corrupt and whole of our operation may gets disturbed.
So will X and Q bar not always be inverted of each other, versions of each other?
No, sir. When this above latch is off and this when this below this tri-state buffer is on, in that case.
So D is no longer driving now.
No, sir. Yes, sir.
D had driven X to some value.
Yes, sir.
And X had driven Q to some value, Q bar to some value.
Yes, sir.
So X is equal to inverted of value of Q bar. X is already
Yes,
equal to that. Am I right?
Yes, sir. But sir, any glitch on this Q bar may change this X. Suppose
Any
if
glitch
some
in Q bar will change. So that is the noise margin of a latch. Yes. So
yes,
that is a different thing. See, that is the noise margin of this latch now.
yes, sir.
So we're talking about an entirely different aspect. But if there is no noise, then there is no problem. Am I right?
Yes,
No
sir.
noise means even if there is some noise which leads to some slight dips, not a glitch. And
Yes, sir.
dips, are you able to see the difference between a dip and a glitch?
Sir, dip and glitch. Sir, glitch will happen in Q bar and dip will happen on this X. Sir,
No. So
sir, just guessing.
no. So glitch means that there is something which is some rise or fall, some transition on the signal is so large that the
Yes.
subsequent stage samples it as a change in input.
Yes, sir.
Okay, that is a glitch. So that is a hazard actually. What happens is Q pe aapne you coupled so much of noise on Q, rising noise on Q, let us say that
Yes.
Q bar, sorry, it's Q bar over here. You coupled so much noise on the Q bar that X actually sensed that Q bar is equal to 0, and then X will go to 1, let us say.
Yes.
So in that case, we say that the noise margin of the latch has been corrupted.
Yes, sir.
Okay, but if someone is within that noise margin, then the latch will restore X to 0 and Q bar to 1 at all times.
Yes. Sir,
Which, if you did not have a feedback, could not have been done. Restoring could not have been possible.
yes.
Sir, one thing, sir. Sir, when you added this buffer in front of transmission gate, you told that there is no back driving disk. And
Yeah.
after that, we added this tri-state buffer. So
Huh.
can this Q bar affect the D at any instance possible?
Now see now, Q bar will drive X through this
Yes.
tri-state, and therefore Q bar can end up driving D also.
Yes.
If there is a situation where phi and phi bar, they have some delay between them.
Yes. So मतलब sir back driving तभी होगी जब ये tri state buffer और transmission gate दोनों एक साथ on रहेगा.
Yes, that is why we just call it a risk. We're not saying it will happen. We're saying there is a risk it can happen.
वो maybe it will depend upon circuit and clock.
It will depend on the timing variation between phi and phi bar.
Okay, sir.
Yes.
Yes.
Okay. Gagandeep?
Sir, this basically this type of latch that you have drawn, back-to-back inverter, this we use in the SRAM cell. So sir, there will kind of largely ignore this diffusion input and all those problems are there also. I'm driving a pass gate in the SRAM cell.
So SRAM cell is a different thing. We will look at SRAM cell when we will cover that topic. Okay. SRAM cell is never driven by a system input. SRAM cell is always driven by something which is within your control as a circuit designer. So you can always characterize it and you can always manage it.
So I know that what is in the proximity of the cell and what are the loads.
SRAM cell is very controlled. It is used in a very controlled environment. So we can do it over there. We cannot do it elsewhere.
Okay. Yes.
Okay. Samyak?
So the tri-state buffer is essentially a better version of transmission gate. So why are we using transmission gate at all.
Yeah. So you can use transmission gates also, yes.
No, I said tri-state is a better version of transmission gate.
Yeah. So sorry, you can use tri-states. So in fact, you will see that in flip-flops, there are transmission gate versions of flip-flops and there are tri-state versions of flip-flops. Both exist.
Okay.
It's more transistors in a tri-state. There's an inversion also happening in a tri-state. So due to area constraints or due to inversion constraints, you may not want to use a tri-state everywhere. So there are both versions that exist. Okay. Yeah, Samyak.
Yes, sir, that's it.
Yeah. So Raghav.
Yes, sir. So there were two properties early in the slides. One was output noise sensitivity and non-restoring. Non-restoring, I get it, but like output, aren't they two linked actually? That output noise sensitivity or non-restoring.
Why?
So can you elaborate on the output noise sensitivity here for this kind of design?
So in this one, output noise sensitivity is not there.
Yes,
because
sir.
output is driven by an inverter.
Yes, sir.
But if the buffer was placed on the input, in this case, there is output noise sensitivity. Hai? When this transmission gate is off, then output is floating.
Yes.
That is what output noise sensitivity is.
Okay. Okay. And sir, in this last slide only, what exactly you're talking about the leakage part? This in the last slide.
Leakage.
So static. This leakage point, sir.
Yeah. So it does that because there are leaking circuits today, and there are let us say if this feedback was not there. अभी तक हमने कहा that X is getting disturbed because of crosstalk noise. What they are saying is that what is being written in the slide over here is that this leakage will also happen, which can degrade X. Either this way or this way, leakage can happen both sides. So because of this leakage, and this leakage becoming actually a big problem today, you anyways need a feedback in advanced technologies. Even if you say my system has no crosstalk, because of leakage, you will still need feedback.
So this leakage problem will be existing for all kind of designs that we have seen till now.
Yes.
Okay, sir.
So this then has a buffered input, which fixes the diffusion input problem, makes the latch non-inverting in itself, and also fixes the problem linked to output noise sensitivity and so on. And this is a situation. So यहाँ पे क्या करा गया? यहाँ पे there is a separate inverter which drives Q. So any noise on Q, see, you're still asking that there is some noise on Q and that can impact X. We were discussing this just a little while back.
Yes, sir. Back
So
driving
to
this.
avoid this problem, what is done is we say that, okay, let us separate the Q buffer. Now, whatever happens here only. This latch in itself is safe. This feedback loop will ensure that X remains at a stable value. But you see, this is so much bigger than the first latch that we talked about. This is so much bigger than that. Clock load has increased so much, but it is still very widely used because it is the most robust one. Is that okay?
So, sir, I just wanted to ask, for example, in the complex gate designing that we're doing, if you're not considering the PTL based design logic, then the diffusion input kind of scenario won't be occurring, right? For us.
If we are not considering the why
For-
transmission gate में भी तो diffusion input है.
So, but like for the static and the dynamic, we won't be getting that diffusion input case because we would be driving the gates only, right? If you're designing the complex gate
Yeah,
itself.
but if you design a complex gate with transmission gates, even then there is diffusion input. That is what I'm saying.
Yes, sir. So,
Not
but
just
that will
PTL, even transmission gates.
okay, right.
So Abhinav,
Hello, sir. Am I audible?
yeah, you're audible.
So, sir, in previous slide, when we are talking about that risk, when tri-state buffer, that feedback part is driving our input D. So we are discussing that if there is any delay between clock and clock bar, then back driving may happen. It might be a risk. So, basically, we are taking clock and clock bar as independent sequence, right? Or we are driving clock bar from clock.
So you tell me, what would you do as a designer?
As a designer, sir, I think clock and clock bar should be independent to avoid that risk. But
It should be independent means, would you put two PLLs there?
Sorry?
Will you use two PLLs there, two clock generators there?
No, sir. But
You will use same
we
clock
are,
generator.
yeah, okay.
So if you have same clock generator, then you have to generate CK and CK bar. Can they be exactly the same phase?
No,
Or
sir.
can they be exactly 180 degrees apart?
No, sir. Okay.
There will be some inverter delay, na?
Yes, sir. Okay.
Hai na?
Yes, sir.
So wherever you are generating clock bar, whether it is in the PLL and then you're routing, making a full clock tree for clock bar also, or you're saying taking clock inside your latch and inverting it there itself and using it. Whatever you choose. Do you realize that there will be some delay?